In this video, we study Fourier cosine series and Fourier sine series. That is, if a function is an odd function, that is f of negative x is equal to negative f of x, then its Fourier series contains only the sine terms. That is something like this. So this is called a Fourier sine series. And when a function is an even function, that is when f of negative x is equal to f of x, then its Fourier series contains only the cosine terms and possibly some constant term. That is something like this. And this is called Fourier cosine series. So let's start. Let's consider a few more examples. Suppose f is a periodic function with a period of 2 pi that is defined by this. F of x is equal to x when x is between negative pi and pi. Okay, since this function is periodic, so what this means is this. So if you plot this between negative pi and pi, let's say this is negative pi and this is pi. This function is just x, so that is something like this. Okay, so not including this point, so this it looks like this. It's just a straight line, but it's a periodic function, so that means this same shape repeats again like this. So this would be, so the period is 2 pi, so this will be pi plus 2 pi, so this is 3 pi, and continue again and again. And same for the opposite side, so something like this, and something like this, and so on. So this would be negative 3 pi here. And as you can see, this is an odd function. That means f of negative x is equal to negative f of x. Okay, so let's say f of so some x is here, and take the negative value of this. So negative x and negative x, and the value of that is negative of this value. So that's what this means. So this is an odd function. And we can generally show that the Fourier series of an odd function involves only sines and there are no cosines. Let's see this for this example. Okay, so let's determine the Fourier coefficients. First, the coefficients of cosines. So this is 1 over pi integral from 0 to 2 pi. And f of x, cosine nx. But this has a period of 2 pi, and cosine nx also has a period of 2 pi. So the product is also a periodic function with period of 2 pi. Therefore, we can just shift the interval here from negative pi to pi, and f of x and cosine nx dx. And now, f of x here is just x in this case, and x, and this is an odd function, and cosine nx is an even function. So the product is an odd function. Therefore, if we integrate from negative pi to pi, so this is the same amount of negative interval from 0 to negative pi and 0 to pi. So they're symmetric, but they just cancel each other. Therefore, the integral becomes 0. And for the coefficients of sines, similarly, we can just integrate from negative pi to pi and x and sine nx dx. Now this is an odd function, and sine nx is also an odd function. So their product is x times sine nx is an even function. So this is an even function. That means we can integrate, instead of negative pi to pi, we can just integrate from 0 to pi and multiply by 2. We have the same result because it's symmetric around the origin. And if you do this by, for example, integration by parts, and you get, you should get, let's see, what was it? This result, negative 1 to the power of n plus 1 times 2 over n. So, in summary, this function f of x, which is x, is its Fourier series is given by 2 times. So when n is 1, we have sine x over 1 and minus sine 2x over 2 plus sine 3x over 3 and so on. The general term is negative 1 to the power of n plus 1 and of sine nx over n and so on. So that's it. And x is between negative pi and pi. And as you can see, there are only sine terms. There are no cosines involved. This is actually a general result for any odd functions. Any odd function can be expressed in terms of sine series. So if f is an odd function, that means f of negative x is negative f of x. So odd function. Then its Fourier series is given by the linear combination of sine functions. So this is called Fourier sine series in particular. In contrast, if f is an even function, if even means f of negative x is equal to f of x, so that means even function, then the Fourier series of f of an even function is given by in terms of cosines only. So that will be something like this. An cosine n of x. And this is called Fourier cosine series. Let's see an example. Consider f belonging to p2 pi. So this is a periodic function with period of 2 pi. And that is defined by this 1 minus the absolute value of x over pi, where the absolute value of x is less than or equal to pi. But this is a periodic function, so this repeats beyond this range. Okay, so let's plot this. X, and let's say this is 0, and when x is equal to 0, it's 1. And when x becomes plus minus pi, then it reaches 0 here. So it looks like this triangle. Okay, and this is negative pi, and this is pi, and this is 1. And so this shape just repeats over and over like this. So this is pi, so this is 3 pi, this should be 5 pi, and so on. And same for this direction. And as you can see, this is an even function. So whatever the value here, let's say this is x, then the value at negative x. So negative x is somewhere here, and the value are the same. Okay, so this is an even function. So let's find the Fourier coefficients. And it's easy to see that the coefficients of sines are 0 by the symmetry argument. And a0 is just integral of this over this range interval, and you can see that it is actually 1. And more generally, let's say pi an is this integral f of x cosine nx dx. And since this is even and this is even, so the product is also even. So we can only consider the interval from 0 to pi and multiply by 2. Okay, and in this interval, the function is given by just x of 1 minus x over pi. And just brute force integration gives you, should give you this. 2 over n squared of pi and 1 minus negative 1 to the power of n. And in this case, n is from 1 to 3 and so on. So when n is even, then this is 1. So it's 1 minus 1 and this becomes 0. So let's summarize the values of an. So that is equal to 1 when n is equal to 0. And it is equal to, when n is odd, then this is negative 1. So negative 1 times negative 1 is positive 1. So this becomes 2. 2 times 2, 4. 4 over n squared pi when n is odd. So 1, 3, 5, and so on. And otherwise, it's 0. 2, 4, 6, and so on. So that's it. So the final expression for the Fourier series cosine series is given by this. 1 over 2, 4 over pi squared. And the first term, 1 squared, and cosine 3x, 3 squared, and so on. Next, consider we have a function g of x on this interval between 0 and pi. So it's not between negative pi and pi, but 0 and pi, okay, only the positive side. Then, based on this function, let us define an odd function, fo of x, by following. So this is equal to g of x if x is between 0 and pi. Or it is equal to negative g of negative x when x is between negative pi and 0. Okay, and also we define this as a periodic function. So x plus 2n pi is defined to be fo of x, and when n is a natural number. Okay, and x is between negative pi and pi. Okay, so for this one, we use this definition. Okay, so in this way, we can define an odd periodic function with period of 2 pi. So here's what we are doing actually. So suppose we have a function defined on this interval. Okay, so let's say it can be any function like this. So this is g. Okay, g is originally defined on this interval, but now, so in this interval, we just use g of x as it is, as given. And for this, so from negative pi to pi, we just copy the mirror of this graph. So it should look like something like maybe like this. So we just make an image. So just rotate this graph around the origin to have this graph. Okay. So that is this part. Then for any integer, natural number n, we define this one. Okay. So the value at here is defined by the value at this minus 2 pi. So it will be something like this one. So we just repeat this and this to, let's see. So like this and this, and repeat to this side and this side. So in this way, we can construct an odd periodic function. Now for this FO, we can find the Fourier sine series. So FO of x may have the Fourier sine series, something like this, sine nx. Okay. But for this one, so for this one, the Fourier series of g of x, which is not really periodic to begin with, can be expressed in terms of sines, a linear combination of sines. And similarly, we can construct an even function, fe of x, based on g of x. So when x is between 0 and pi, we have gx, and when x is between negative pi and 0, we just define g of negative x. Okay. When x is negative here, then negative x is positive, so we can use this value. Okay, so it's symmetric around the y-axis. And also we can introduce the periodicity to n pi equal to fe of x when n is a natural number and x is between negative pi and pi. For this one, we can use these values. So if we have a function g of x defined on this interval between 0 and pi, then we can just make a symmetric mirror image around the y-axis to have something like this. And then we repeat the same pattern over and over, and so on to this side also. Then we have an even periodic function for which we can calculate the Fourier cosine series. That is fe of x. So Fourier cosine series would be something like 1 over 2a0 and an cosine nx. So when nx is between 0 and pi, then we can say g of x can be expressed, the Fourier series of g of x can be expressed in two ways. That is, first as a sine series, Fourier sine series, and sine nx, or as a cosine series. In two ways.